Welcome to session 2 of the Intro to AI-Driven Science on Supercomputers. Again, my name is Paige Kinsley. I'm the Education Outreach Lead at the Argonne Leadership Computing Facility, which is the host and creator of this workshop series. Today, the focus is going to be on neural networks and introducing sort of the fundamentals. The speaker and instructor today is Marieme Ngom, who is an assistant computer scientist here at ALCF. I'm going to hand things over to Marieme so she can introduce a little bit more about her background, both in her studies and scientifically, and then we'll get started from there. So, Marieme.
Thank you, Paige, for the introduction. So as Paige said, my name is Marieme Ngom. I'm an assistant computer scientist at ALCF in the ML and data science team. I've been mostly working on LLM optimization and also on uncertainty quantification for ML. And my PhD was on pure applied math from UIC. I did my PhD on partial differential equations. Okay, so as I said, I'm going to give you an introduction to neural networks. So today, the objectives of this session are twofold. I'm going to introduce the fundamental concepts of deep learning through hands-on activities. So the goal is to give you the necessary background for the more advanced topics you are going to learn about in the upcoming weeks. So last week, you worked through a linear regression problem to predict the sale price of a house. So you had as input things like above ground square feet and as output sale price. And you fitted a linear function using the stochastic gradient descent optimization algorithm with the mean squared error loss function. And this week, we are going to work on a classification problem with the MNIST dataset. So I'm going to tell you what is classification in a couple of slides. So first, let me talk about the MNIST dataset. So it is a dataset that contains thousands of examples of handwritten numbers with each digit labeled from 0 to 9. So these numbers were obtained from high school students and employees of the US Census Bureau. So for example, here you will have things like an image of 0 with the label, the corresponding label 0. So this week we are going to do classification. So as you may know, we have three main types of ML algorithm: supervised learning, which is when your data is labeled and you know the correct output. Unsupervised learning, which is the opposite of that, which is where you are learning patterns from the data without the label outputs. And then semi-supervised, which kind of mixes both approaches. So this week we are going to do classification, which is a supervised learning task, where the goal is to predict the categorical label of an input based on its features. So for example, here, the input would be the image of a handwritten number, 1, for example. And our goal is to build and learn a function or model F that will tell us, oh, okay, so this image is probably 1, or it might make mistakes and tell us it's 2. And we're going to see how to build such a function and how to evaluate it. So as last week, we are going to work on Google Colab. I think Paige shared a link to the GitHub. So here we're going to do Google Colab. Okay, so you go to File, Upload Notebook, GitHub, and you enter Argonne LCF. And then you scroll down to AI training series here. AI science training series, and you pick the third one. There you go. All right, I'm gonna just wait for a couple of seconds here, just to make sure that everyone has their notebook open on Colab. Please do let me know if you are having trouble opening it. You do need a Gmail account, but I think that was dealt with last week.
Marieme, will you zoom in just a little bit on your screen, just so we can see some of the code?
Is this better?
It is, thank you.
Okay. All right. Okay, so as I mentioned, we are going to work with the MNIST dataset. We are going to use the PyTorch library, which is built on Python and which is pretty extensive, that has all of the functions, models, and all of the things we need to build a machine learning model. And that also allows us to build custom models and custom tasks and functions. So we're gonna start by importing PyTorch, NumPy, Matplotlib for plotting and all of that. The first thing we are going to do is download our dataset. The MNIST dataset is a very popular dataset. Some say it's the hello world of machine learning. So it has inputs that correspond to the images of handwritten digits, and labeled outputs like this are just the numbers 0 to 9. And the test can be split into training and test dataset. So if you run this code here, it will take some time for you to run for the first time, so you should do it now. So to get the training dataset, you set the parameter train here to true, and to get the test dataset, you set it to false. So the data has 60,000 training examples and 10,000 test examples. So each input has 28 by 28, or like 784 features, which are just the pixels. So going from 0 to 1, white to black pixels. I'm just going to give you like 10 seconds, because this can take some time if you are doing it for the first time, to load the training and the test dataset. So this is pretty, you can do that directly on PyTorch, which is like great of accessing all of these popular datasets that we use in machine learning for testing. Okay, so what we are going to do next is split the training dataset into what we are going to use for the actual training and into a validation set. So this is good practice. This will allow you to assess the quality of your model as you train. So this will let you see if you need to switch some parameters of your model and change your model, change the learning rates and things like that, as I'm going to show you later. So we're gonna set 80% of the training data for the training, and then the remaining 20% will be for validation. So you can see here, now we have 48,000 examples for the training, 12,000 points for the validation, and 10,000 points for the test, each having 1 by 28 by 28 size. So you can take, we can take a look at the data here. As I mentioned before, it's just images of handwritten digits with the corresponding classes. So here 1 and the class 1. So to build our model or our classifier, we need, of course, the data, and then we'll need to build a model that will depend on parameters theta. So here we are going to use neural networks, which are models that basically mimic biological networks. We are going to build a loss function J to measure the capabilities of the model. So the loss function will depend on the parameters theta. And we need also an optimization method that will allow us to find the theta that will minimize our loss function. So today we are going to start with a linear model. Last week you did linear regression. Today we're going to do linear classification, and I'm going to show you how you can write a linear model as a network. So here in PyTorch, you have a linear model. A simple linear model can be obtained by having inputs, what is called an input layer here, and an output layer, and each layer has nodes or neurons, if we borrow nomenclature from biology. So you have neurons here in the input and the output layer, and from the input to the output, you have these connections with weights. So the linear layers in PyTorch will perform a basic operation X, where X is your input, times W. W will be the weights of your network, and plus B. And B is a bias term that gives you more flexibility. So last week you were doing regression. So you had just this simple XW plus B and the mean squared error. So this will not, that would output numerical values like 3.5 or 2.1. But here we are trying to predict integers. So we need to do more than that. And that I'm going to talk about that in a couple of minutes. So we now need a loss function. So as I said last week, mean squared error, but this week we are going to make some changes to be able to do classification. First, we're going to change the output to be a 10-sized vector of class probabilities, meaning if I have my model and I feed an image to it, I want to output the probability of this image being 0, 1 to 10, 2 to 9. So 10 probabilities. Here we are going to use the cross entropy loss function, which is a typical loss function used for classification. And you can read more about it on this at this link here. You have more details about the loss function at this link. Now we need an optimization method. Like last week, we are going to use stochastic gradient today, but you can use more advanced optimizer like Adam or Adagrad. Again, some references for more details about these optimizers. One thing to keep in mind when doing, when setting the optimizer is the learning rate. I think last week Hugo showed you how the learning rate controls how far you move during each step. So having a good learning rate is key to training a good model. So we are ready to define our linear classifier on PyTorch. Here it is, it inherits from the nn.module class. And then to build a simple linear model, we're going to do these two functions. Flattened, meaning we are flattening our input by setting the second dimension, which is 28 by 28 to 784. And then we are going to add a linear layer. So that will have 784 input nodes or neurons, which correspond to the pixels of the image, and then 10 output nodes, which corresponds to the probabilities of each class. So we're also going to define a forward method, which performs this operation. We flatten the input, then we do the linear operation, and then we return the output of that. So here we are going to instantiate a linear classifier. We're going to call it linear model. And we are defining the loss, the cross entropy loss, and the stochastic gradient descent optimizer with a learning rate of 0.05. Now, to train this model, we need to do a training step, which is comprised of a forward pass, which is just this operation here. After the forward pass, meaning that the input is passed through the network, we do back propagation to compute the gradient of the loss function with respect to the parameters W, and if you have bias, B of the network. After doing back propagation and computing our gradient, we can do the weight updates, which is this formula here. You update by doing W equal W minus alpha times the gradient of the loss function with respect to the parameters W. Alpha here being the learning rate. A first question that you can ask yourself is how many steps to take. To define the number of steps to take, you can set a batch size which corresponds to the number of training example in one full pass being forward pass and backward pass. So if you do a smaller batch size, that means the model will learn from individual examples, but will take longer to train. And if you pick a large batch size, you will do fewer steps, but your model might fail to capture the nuance in your data. And the higher the batch size, the more memory you will require. So batch size is a very important parameter that needs to be tuned carefully. Another word I would use here is epoch. Epoch means one pass through the whole training, meaning you have looked over all your batches. So if you use a small number of epochs, you can have a phenomenon that is called underfitting that I'm gonna explain later. And if you use too many, you can have the opposite of that, which is called overfitting. Again, the choice of batch size and of learning rates are very important for performance, for generalization, and for accuracy when you are doing deep learning. So here, let's pick a batch size of 128, and we are going to use the data loader utility to make our dataset iterable. So this will just allow us to be able to iterate through our training and validation data. We are now ready to define our training function. So we're gonna have the parameters, we're gonna have the data, the model, the loss function, and the optimizer. The first thing we do is set our model in training mode by doing model.train. Then we are going to iterate through our data set, perform a forward pass to get the prediction from our model, compute the loss function between the prediction and the exact output, do a backward pass by doing loss.backward, and then update our weights. So taking one step with these gradients by doing optimizer.step. And then we reset the gradient, and then we iterate until we have reached our number of epochs. We also need an evaluation function. So to do that, we set our model in evaluation mode. We don't really need to do that here, but it is good practice to set your model in evaluation mode when you are evaluating. And then we are going to compute the number of correct predictions in each batch and also the loss. And then we're going to have the accuracy of our model and the loss of our model. We are ready to train now. So this time here is just to compute our runtime for the training. We are going to do 5 total epochs, meaning we are going to iterate through the whole data 5 times. And then we're gonna do in each epoch, we're gonna train and we're going to evaluate. So I'm going to evaluate on here I'm looking at the training loss and training accuracy, and I'm also showing the validation loss and validation accuracy. So as you can see, we are starting at 87%. We are at epoch 1, 88%, almost 89% on the training loss and 88.8 on the validation loss. And it's keep going, it's learning, it's gonna do this for 5 steps. Again, if we were like doing hyperparameters tuning, so the hyperparameters being things like your learning rate, your batch size, or things like that, having the validation loss and validation accuracy is important. Okay, so we are done training now. We have reached an accuracy of 90% with a loss of 0.35 on the training set. And here we can see the training and validation accuracy with respect to the epochs. So you can see the validation accuracy is a little below the training accuracy. It's not too far from it, but still, and this if the difference was like wider than this, that could be something to spend some time on. That could be a symptom of what is called underfitting here, meaning that maybe our model is simple for this data set. So we can show here how the model is doing on the first 10 examples. It's doing pretty good. It's predicting all of the classes correctly. 1 is 1, 0 until 8. And here you can improve the accuracy. It's 90%. You can improve it by maybe adding more epochs or changing the learning rate. So if you want to take 1 minute maybe to do that. If you are doing a lower number of epochs, you might have to redefine your model here. You might have to run this again, because otherwise it's gonna start from the last, from the model you had after training for 5 epochs. So you can see if you are improving or making your model worse. All right. So now we can do some prediction. You can see how your model generalizes to unseen data. Remember, we set some of the data aside, and our model has not seen it yet during its training. So we're going to load the test data and make it iterable using data loader. And we can evaluate it now and see how the model is doing on the test. It's doing, it's pretty on par with what we had during training, 90% with the loss of 0.33. We can take a closer look at the results by showing the failures. So here, this function is just a helper to show the first 10 failures of the model. So let's see when the model is failing to predict. Show failure. Okay. So you can see here, this sees a 5 that it predicted like a 6. This one kind of makes sense, because if we didn't have this line here, it's pretty close to, I mean, one could understand why the model could mistake it for a 6. You have this 4 here that was mistaken for the 6. This one might be a little bit harder to see. If it was like a human might not make this mistake. It maybe someone could have said, oh, this might be a 0 if we just had a line here. This one also was mistaken for a 3. So this can be a sign that our linear model maybe isn't complex enough or like accurate enough on this data set, and that we might need to improve it. So to improve a neural network, what is usually done is adding more layers and nonlinearities. So here I'm showing a simple shallow network with one hidden layer. So remember before we had an input layer and an output layer. Here we are adding one hidden layer. On top of that, we are adding nonlinearities, sigma 1 and sigma 2. So these nonlinearities will make it possible to learn more complex tasks. So here you have a 3 layers network with one hidden layer and activation functions sigma 1 and sigma 2. I'm gonna talk about activation functions in a while. So the output of this layer would be the output. So first you compute the output of the hidden layer, which is this inner operation here, xw1 plus b1, to which you apply the activation function sigma 1. And then you act as if this was your new input, and you do the same with the activation function sigma 2. So you can see how this is more complex than just doing xw plus b. So activation functions are, the choice of activation function is very important. You have many actually universal approximation theorems that tells you that you can approximate with a neural network, you can approximate any continuous function in a compact domain using non-polynomial activation functions. So the choice of activation function is important. Some desirable properties in an activation function include them being differentiable. Differentiability is important for the optimization. Methods like gradient descents and stuff works much better or works well with differentiable functions. Boundedness is important, and monotonicity is important, meaning that you want your function, usually it's increasing. But these are not required, as you will see on these examples. These are the most commonly used activation function. One that is very popular is the ReLU here. That is that works well with images. One thing about a ReLU is it's not differentiable at 0. So you have approximations like the GLU, which are like differentiable approximation of ReLU. Another very popular activation function is the sigmoid function, or like the tangent hyperbolic. So you can see, again, these are differentiable, bounded, and increasing. But as I said before, it's not, you don't have to, it's desirable properties, but it's not like a requirement. You can basically have any, you can have a sine function if you want, or custom activation functions. All right. So to obtain a deep neural network, you just add more layers. So anything that's less than 3 layers is usually called the shallow network. And if you have more than 3, it's a deep neural network. Deep, so the depths correspond to the number of layers on your network. And another term that's used also is the width of the networks, which corresponds to the number of neurons in each hidden layer. So again, you don't have to have the same number of neurons in each hidden layer, and you can have also different activation functions. Here we are going to use the same activation function and the same number of hidden nodes, but it's not a requirement. Important things to keep in mind when training a deep neural networks are as follow. You have to, deep neural networks can be overly flexible and complicated and overfit your data. I mentioned overfitting and underfitting before. So a good way to showcase underfitting and overfitting is looking at polynomial interpolation. So here, for example, we have this data set, these samples that correspond to the blue circles with the true function. This is the orange curve here. So if we do a linear model, we are oversimplifying the model, meaning we are underfitting. And if we do, for example, something with degree 15, we are doing very well on the samples, but we are making the problem too complex. If we were like predicting, for example, a point here, we would be way off. So this is this describes the overfitting phenomenon well. So what you want to do is a balance between the two, which is called the bias variance trade-off. So here, a polynomial with degree 4 would have been perfect. So you can see this underfitting and overfitting phenomenon during training if you look at your validation and your training accuracy and loss. So here, for example, if you look at the number of epochs, if you stopped before this red line here, your model would have underfitted the data. And if you went, if you used much more epochs than that, you would have like overfitted your data. How do you see here how the training accuracy is much higher than the validation accuracy? Same for the loss here. The training loss here is much lower than the validation loss here, which is something you want to avoid. So what you want to do is be somewhere in between, a middle ground, which would correspond here to stopping at this red line here. So tracking the validation, having set a validation set, a validation data at the start and tracking validation loss and validation accuracy will allow you to incorporate strategies like early stopping while training. You would have stopped here instead of going, and having the validation loss and the validation accuracy would have allowed you to see that. So techniques you can employ to improve the generalization of your model to unseen data include things like regularization, which constrains the model, which constrains the optimization problem to discourage complex models. So one regularization technique is dropout, meaning that you randomly set input units to 0 with a frequency at each step during training. So this will help you prevent overfitting. Another very popular strategy is like penalizing the loss function by adding a term such as lambda times the norm of the weight squared. So this will allow you to control the magnitude of the weights of your network. And this is also something that is used to prevent things like exploding gradients here. Exploding gradients is something that can happen when during backpropagation, your gradients grow exponentially. And this is usually due to poor weight initialization. So that's also something you need to keep in mind when building a neural network is the weight initialization. So here we are using PyTorch that has a default weight initialization that works well here, which is the k-mean initialization. But if you are doing something else, you might want, and your model is not converging, and you are having like things like nams or big gradients, you might want to look at the initialization. So that is exploding gradients. You have the opposite phenomenon, that is vanishing gradients, which is when gradients become small as they propagate backward. And this can be caused like things like the activation functions. For example, here, this squashing activation function, sigmoid or tangent hyperbolic, can make your gradient small. So if you have something like this, you might want to explore more activation functions. So we are ready to implement a deep network in PyTorch. So here we are going to use the dropout operation that I've just mentioned. So here we are going to build a nonlinear classifier. As before, we're going to flatten our input, and we're going to use this NN sequential function, which just stacks layers. So here we are stacking one linear layer. We are doing the value activation and doing a dropout at 0.2 late. Then we have a hidden layer with 50 neurons, and we do a ReLU activation as well. And we repeat that. Let me implement this dropout thing here. And then at the end, as before, we need an output of 10 nodes, which corresponds to the probabilities. As before, we are going to use the cross-entropy loss and the stochastic gradient descent optimizer with a learning weight of 0.05. We are also going to do 5 epochs, meaning we are going to go through our whole data 5 times, and we are going to track things like the validation loss and accuracy loss, as well as the training and accuracy. The training loss and the training accuracy. Okay, so this will take more time because our model is more complex. We have more layers, more neurons, so more work to do. So here we are starting at 74% accuracy and a learning loss and a loss of 0.88. You can see it's increasing. This is a pretty sharp increase as it's learning. It's at epoch 2. It's already at 91% accuracy. It's going. It's gonna take like maybe 30 more seconds.
Marieme, there's one question that's in the Zoom channel that popped up. I know there have been a couple in Slack that have been answered.
Okay.
But Jennifer in Zoom asked, is this example bidirectional, like a BERT model?
Oh, no, this is, what do you mean bidirectional? Are you talking about the encoder, decoder? It's like, it's much less complex than BERT and all of that. So if by bidirectional, you mean, it's not the same like beast, if I can say it like that. So this is just a simple neural network where you go do forward and backward. So in this sense, maybe you can say it's bidirectional, but it has nothing. It's not like the BERT model. I'm not sure.
Thank you.
That's what you mean. Maybe someone else can.
Yeah.
Yeah. In that sense, you do a forward and a backward, but it's not like the same spirit as what BERT does.
Yeah, I guess my question wasn't like
yeah.
it had like each node was connected to another layer, like.
Oh yeah, so each node is going Each node is connected to the layer in front, and then you can in the back also. I don't know how to say it. So you have forward, and then you're gonna do also a backward pass. In that sense.
Yeah.
Yes. Okay, so now the training is done. We have reached 93%, which is an improvement from before. We can look at the training and validation accuracy. So you can see it's much more, the validation and the training accuracy are much more on par as compared to before here. You can see this gap there. And then as before, we're going to see the first 10 failures. We have this 4 again, but you can see that the failure now makes kind of, this 4 and this 9 kind of makes a sense, right? Because this look like a 4. This 8 also, if you just close this gap, this would have been an 8. And you can like improve. You can try to see if we added more epochs, what would happen. So here I'm going to do 2 because my model is already at epoch 5. So I guess if I do this, it should start at 93%. It'll take some time. Yes, so let's see. We have to also be careful not to overfit. But 94% is still fine. So 95. Okay, we can see the validation accuracy is still on par. It is. Okay, so now we started. So this is, you can't really say anything about it because we started after 5 epochs. So if I did, I kind of started over. So this doesn't mean what it shows, but let's see the first 10 failures here. So you can see different failures here. And I guess you can make your model better. You can play with this. You can use Adam here and see. Adam is a more advanced optimizer. You can use Adam and see what will happen here. Let's do Adam and see. Again, it's going to take some time because our model is more complex. So 84. If you have questions while it runs, don't hesitate. 6%.
One question that was asked is, how can we tell how many layers are necessary, which has been asked a couple of times now.
Yeah, so you can do what is called hyperparameters tuning. So you can have like, before you decide on a model, you can pick many different layers and do some pre-training to see which one works better for you. And then you pick that one. It can be expensive, but it's what's called hyperparameter tuning. So you can do that not only for the number of layers, but for the batch size, for things like the learning rate of your optimizer. To set also the learning rate, one very popular thing to do is use a learning rate scheduler. So you can look that up. So it's how you usually set your hidden layer nodes, or the number of hidden layers you have.
So one other question that was brought up that I think you sort of just answered, but I wanted to confirm, is that asking like, how do we know when you've like reached the balance iteration, right? How do you know when you've finally, to prevent underfitting or overfitting, how do you know when you've like definitely reached sort of the sweet spot?
So you can track your validation and your training loss. So you can do something that's called early stopping. If your loss stop improving, or if your loss start getting worse, like for example here, you stop. So here you can, if you track your validation loss, after this point you see your loss is starting to get worse again, to go higher. So you would want to stop here. So usually you can do you can stop on plateau, for example. When it's plateauing here, you can add some more lines of codes to make it stop before, to make it stop at this exact sweet spot. So that's why it's important to also have some validation while you are doing the training. Okay, so here using Adam, you can see Adam after 5 iterations, it's like at 86%, but probably because the learning rate is kind of high here, if I reduce that. So you can see like all of these important things. Or maybe I need to add more epochs, we'll see. So you can see like how you need to, you can do this automatically. You don't have to go on and do it manually. Normally you would have, again, when you do hyperparameter tuning, you can have many type of optimizers, many type of learning rates, many number of layers, batch size, number of epochs, so you can know which one to pick. So you have this. So this is usually, this is also doing the dropout. So again, you can see this one after 2 epochs, it's already at 94%. Okay.
Maybe one other question while we're waiting.
Okay. Yeah.
Someone asked, how do you decide on nonlinear versus a linear model for this kind of classification problem?
Oh, so usually if your data set, if you know your problem, if your data set is simple and stuff, you can try maybe a linear model and see if it works. But nonlinear, if your data set is a little bit complex, or if you want to learn like nuanced things in your data, or like more patterns, you might want to do nonlinearities. Add some nonlinearities. So and then you can play with the activation functions. So for example, I like working with periodic data and periodicity. So using sine and cosine, using periodic activations with some more like tweaks on the loss functions can be helpful. So if you look at your data, if you are doing supervised learning, you look at your data beforehand, you might have an idea of what type of model or what type of complexity you need for it. I would say start simple, maybe a shallow network, one hidden layer, like I usually start with 16 nodes in the hidden layer. But you can do that. And again, you can automate it, and you have tools like, I don't know, at Argonne we have Deep Hyper, I think. PyTorch has RayTune, and all of that can be used to kind of decide on your hyperparameters, which are things like, as I said many times now, all of these parameters of your model that you can, that are prefixed, like the number of layers, the nonlinearities, and things like that. Okay, so this one with Adam and a smaller learning rate finished. So this is kind of, I would say, a large gap here. And then if you look at it only predicted. So here we are trying to see the 10 first failures. So it only has 6. So you can see that you can play. You see all of these parameters that are important, learning rate. I've played with the learning rates and the optimization. You can do batch sizes, number of epochs, and all of that. And keep in mind overfitting, underfitting, the initialization. Here we are using the default initialization, which works well, but sometimes you have to use like Xavier initialization and things like that. So these are like things you need to keep in mind. So to summarize, so to train and validate a neural network model, you need your data that you're going to split into training, validation, and the test set. So the test set is the part that you keep, that the model will not see, and that you will use at the end to see how your model generalizes to unseen data. You need your model with parameters like the weights and the biases that you're going to learn. You need an appropriate loss function. If you are doing regression, the loss function you had last week, which was the mean squared error, would work usually. But here we were doing classification, so we use the cross entropy loss. And you use an optimizer, so SGD, Adam, RMS prop, that has tunable hyperparameters like the learning rate, weight decay. The homework has some question about weight decay, and that you use this optimizer to learn the parameters of the model. And you can do all of these things I show you to assess the quality of your model. So I think we have some time. So if you wanted to do, so here, as I mentioned, we used dropout to make sure that our model is not overfitting. So you can play with this. So you can turn it off also to see. So here is dropout. This is what we had. Let's see what will happen. 96%. Let's see what will happen if we don't allow for dropout. So again, you can ask questions while it's running.
Let's see. There are lots of good questions that are coming more. One person just asked, can you explain more on weight, the weight decay parameter and when to use it?
Yes. So so the weight decay parameter, so here it's when you penalize. So this lambda here is the weight decay parameter. It's when you penalize your loss function by adding a term. So cross entropy loss plus lambda norm of W squared. So this norm, the choice of the norm is also important. You can use, if you are familiar with matrix norms, you can use the L2 norm. So the L2 norm will just make sure that your weights are like small, or you can use the L1 norm. So the L1 norm will push your weights to be closer to 0. It's more like you are like turning off some connections. So this will allow you to avoid things like overfitting by making your weights reasonable. But also it's very important for avoiding this thing called exploding gradients. Exploding gradients is what happens when your weights grow too big and the gradients like are just too high, and then you don't converge. You will usually have like very large gradients or like nuns. So having this weight decay term here will allow you to avoid this exploding gradient phenomenon. It's actually pretty common to use it, and it's in PyTorch. It's very easy. You just add weight decay here to your optimizer, and for example, do something like this: 1 to the -3. You don't want it to be too high, and you do it like this. So that's how you add weight decay. So you can see 95%. Okay, you can see the drop here is even higher without the dropout, the regularization. Yeah. Let me look at, so we had 6. Now we have 7 failure, but I'm not sure it's like meaningful at the scales, but you can see like the small differences here that having this on or off can cause. So we can also try now without dropout, but with the weight decay. I think 1 to the negative 3. Okay.
Another question while we're letting things go. Why is the training effect better when we use a multi-layer model?
Why is can you repeat?
The training effect, like why is it better trained when using a multi-layer model instead of just a single?
Oh, because you are making your model more complex. So you have like more parameters, more non-linearities. So you are like able to learn more complex things. It's working here, but if your function was simpler, for example, your training would have been very good, but generalizing would not work. You see, like here, for example, like having a degree 15 corresponds to having, like, I don't know, more layers in your network. You would do very well in training, but in predicting, you would do much worse. It's like you are just, like overfitting is such a perfect term for it. You are trying to get your data exactly. So you are putting more noise, more like oscillations and all of that by adding more non-linearities.
And then one more question in reference to sort of the dropout function that you were talking about earlier. Someone asked, instead of using dropout, why can't we just change the training and validation ratio to say like 0.7 and 0.3?
Instead of using, okay, so dropout is kind of turning off. Okay, so there are 2 things. So having a validation set, if the validation set is much smaller than the training set, okay, that might make it hard to see how the validation loss and training loss like interact with each other. That is a good point. But the dropout is not. The dropout is setting the units. You are dropping out some connections. You will still have 784 input nodes. You see what I mean? But you are dropping some connections. Like in the input, you are dropping some. If you had 50 hidden nodes, you are dropping some of those connections. I'm not sure if having a lesser training set doesn't really change that. You need more. I mean, the more data you have, usually the better, actually. So. But you might you should pay attention. You don't want to have a validation set that is much smaller than the training set. I don't know.
Great, thank you. So I know we have a couple other good questions in Slack, but I want to make sure that you obviously get through all of your content.
Yes.
So I'll let you do that, and then if we have time, we can continue to do more of a Q&A.
Okay. So I think I did the weight decay. So I'm not sure if I did the weight decay. I showed the weight decay. This is at 73. I think I did. Let me see. Yes, so with the weight decay, I mean, the failure is different. So this 4 was a 2. You can see here, the discrepancy is less than when we were doing dropout. So you can see like which strategy maybe to use. Again, these are things that you can do when tuning. I mean, when picking a model, when setting your model parameters. That's all I had. And in the README here in the GitHub page, you have some pretty good references. On TensorFlow, today we showed PyTorch, but TensorFlow is another framework that is pretty popular for neural networks. Keras, I think, which is now kind of embedded to TensorFlow. And you have all of this. You're going to learn about convolutional neural networks, I guess, in the upcoming weeks. And you have all of these like references, courses, and tutorials, and some references to this book here that I have. I mean, I like having physical books, but this is a very good. This is a very good resource for learning the basics of machine learning. It is with TensorFlow, but still it has like very good resources and explanations and notebooks. So it is a very great resource. This hands-on ML book. Yeah, that's all I had for today.
Before we jump to more questions, will you just go over briefly what the homework will be for this session?
Yes. So the homework will be, we did some of it, but I just wanted you to play with different batch sizes, learning rates, and activation functions here. We are doing ReLU here, which is pretty good for images, but I would like you to try more activation functions. And a bonus question is if you can tell me, I mean, 2 or 3 sentences about what a learning rate scheduler is. Maybe do some research on what is that, because it's an important tool. And I think you will see it in a couple of weeks. So it will allow you to know when our instructor will talk about it, what is the learning rate scheduler. And that's it.
Great. I think we have maybe 5 or 10 minutes for questions. So like for participants, like if there are things that have been sort of in your brain that you'd like answered, obviously drop them in Slack. Also, you're welcome to unmute if you want, if you feel like you dropped something in Slack, but you didn't get a good answer or you want more answers. But one question that was dropped in Slack that I think is a good general question is, how do you divide the data for training validation test?
Okay, so usually it's 0.8, 0.2. So 0.8 for the training and 0.2 for the test. But then if you do validation, you might want to do 80% of that training set for training and 20% for validation, and then the remaining 20% is the test. Or you can do 0.7, 0.2, 0.1. So you want the common trend here is much more data for the training, and usually you have 20% of the test for the testing, and then you divide the training into the thing you actually use for training and for validation. So 0.8 training, 0.2 testing.
Another question, are the learning rate scheduler and an optimizer synonymous?
So the learning rate scheduler is something that's used to set the learning rate for the optimizer. So the optimizer needs a learning rate the learning rate is used here to update your weight. It doesn't have to be constant and stuff. So you can make it, you're using a learning rate scheduler. So as you go through your training, the learning rate scheduler will take care of how this alpha changes.
Another question, can the early stopping criteria be implemented in PyTorch automatically, or do we need to keep track of validation error manually and select the corresponding train model ourselves?
I don't want to say no, but okay, so when I was doing early stopping, personally, I would just add it or stop on plateau. I think there is if you do optimizer.scheduler, maybe someone can answer quickly than me. I think you have something that can make it stop on plateau, like automatically. I'm not 100% sure. You can definitely do it manually. But I believe there is something that that you can stop like on plateau and things like that. Yeah.
I think you can just add a counter.
Yeah.
Okay, couple more questions. People, all of these questions are amazing. Well done, everyone. Okay, question, is there a way to choose the activation function which works best, or is it always just parameter tuning? I think you talked about this a little bit at the beginning.
It's, yeah, so so I would say if you have like all of these softwares that allow you to do hyperparameter tuning where you can change, definitely you can put like many choices. But if you are like a domain scientist and stuff and you know your data, you might know in advance what might work better for you. As I said, when I do differential equations that are periodic and that are usually solved with Fourier and stuff, I know that using sine or something like x plus sine or whatever would work. So I'll just do that. If I know that my output is bounded between 0 and 1, I can put sigmoid or something at the end. So if you know your data and you know your task, what you are doing, if you are like a domain specialist or something, you might be able to define it beforehand. Pick one that works good, that works well.
Another question, this may be one of the last ones, but someone asked, if you use cross-validation for optimizing your hyperparameters, do you need to split your data in training and testing, or is it enough to just do the cross-validation itself?
You always need you need to do training and testing because you want to see how your model does in something it hasn't seen at all yet. See if it generalizes and stuff.
And then another question that just came through, should we normalize our data to work with activation functions?
Not normalized to work with activation function, but normalizing might be a good idea. Usually, sometimes for some of these models, you want your data to be between 0 and 1. And like when you do also neural networks, there are some operations, I guess next week you're going to learn about them, like batch normalization and all of those things that will make your model work better. Yeah. So you might want to, yes, before feeding it to the network, normalize your data sometimes. I mean, batch normalization is something else, but yeah.
Great. I think we'll pause now based on just the content that you shared. So thank you, Marieme, for the information that you shared. Thank you, everybody, for all of the engagement and the questions. Of course, as you continue to work through things and as other questions might come up while you're doing the homeworks, feel free to drop them in Slack and we'll have folks answer. Right now, we have a good combination of both participants and ALCS staff that are answering questions. So keep on doing that. That's great. So thank you so much, Marieme.
Thank you, and thank you everyone for the questions.
Great. So now we're going to switch over to our AI for Science talk for today. So I want to introduce our speaker. So our speaker today is Nina Andreevich. She's a Maria Goeppert-Mayer Fellow at Argonne National Lab, which is named Fellowship at Argonne. Her research focuses on developing physics-aware machine learning models to assist the analysis and interpretation of materials characterization data. She received her bachelor's in engineering physics at Cornell and her PhD in material science and engineering from MIT. Alongside her research, she's also enthusiastic about science communication through teaching and scientific data visualization. And today she's going to be talking about advanced materials characterization through physics-guided machine learning. So with that, I will hand things over to you, Nina.
Thanks, Paige. Let me share my screen here. All right, can you see my full screen?
Looks great.
Okay, great. Thank you so much. So hello, everyone. As Paige said, my name is Nina Andreevich. I'm a postdoc fellow at the Center for Nanoscale Materials here at Argonne. And so today I'll be talking a little bit about using physics-guided machine learning methods to model and understand materials characterization data, which is the area of research that I'm in. Very broadly, this idea of data-driven modeling of materials characterization data, so certain observables that tell us about materials behavior, this kind of arises in the context of two main objectives in my research. So the first one that I'll be talking about is using neural networks to help model some key properties of materials directly from certain accessible inputs that we have about them, like atomic structures, and to thereby accelerate the prediction of these properties compared to some conventional techniques or experimental measurements. And then the second direction that I'll talk about is using some type of, again, a data-driven analysis or machine learning model to help extract additional insights directly from experimental measurements of materials that maybe we can't get using theory or is very difficult to obtain directly through theory. All right, so in the first example, the machine learning models are primarily functioning as sort of surrogate models for some more intensive first principles calculations of materials properties that we get from their atomic structures. And so by having a machine learning model, this can generally allow us to do two things. One is to do some kind of high throughput screening for materials that have certain targeted properties, or it can also be used, again, as some kind of a surrogate model that's going to help us invert this characterization data back to atomic structures, which were previously unknown. And so this would be part of some larger loop to invert that data. However, one thing that we encounter, at least in my field, when dealing with materials data, is that a lot of the times, both the calculations, the first principles calculations, as well as the experiments can be pretty expensive or scarce. And so we don't have millions of training points, which we typically need when we think about training a very good machine learning model that's going to generalize really well. And so one thing that we want to do in this case is to kind of balance this trade-off between data and domain knowledge. So we're going to incorporate some physics into our neural networks in order to make them more data efficient. So be able to learn from less examples than we might typically need. So how do we go about achieving this? So the strategy that we used kind of falls under this broad class of equivariant neural networks, which you may have heard of. So in particular, the network architecture that we use is called Euclidean neural networks, and I'll explain why. But just to kind of overview sort of what are our inputs, what are our outputs, how does this all work? So as I mentioned, our inputs are some accessible properties about the material. So things like, so we encode these actually as graphs. And so things like the atomic masses get encoded on every node of the graph. And then things like displacements between nodes between atoms in a crystal get encoded on the edges of the graph. And so these things get passed in as input to the neural network. And then over here on the output, we have some predicted quantity. So here it was a vibrational spectrum known as the phonon density of states. And so how do we now incorporate the physics that we were talking about? So in particular, with these Euclidean neural networks, as I mentioned, what allows them to be data efficient is that we impose certain expected symmetries on the different layers that are acting on our input features. And specifically, what we do is constrain these layers to be equivariant to Euclidean transformations, so E3 functions. So this means that in this context, what equivariant is telling us is that if I apply some kind of a translation or rotation to my coordinate system that I use to represent my crystal structures, and then I pass it to the network, it's the same thing as if I pass the system in the original coordinate system and then transpose my output using that same transformation. And so the reason that this is helpful for our case is you can think of it as kind of constraining the optimization space of functions that our neural network needs to learn. And so because we have a more limited space using the known physics, we're then able to kind of train the network more effectively, even without as much data. And so I don't have time to go into a lot of detail about exactly how this works, but if you're interested in looking into sort of more of the nitty-gritty of this, I recommend looking at these references for sort of what is the kind of the trick that makes these networks work. But just to kind of highlight what we can do with this, so we had a pretty limited data set of around 1,200 calculated examples of these density of states spectrum. And then we trained this Euclidean neural network. And so here on the bottom right, I'm showing an evaluation of that network on some unseen examples, so things from your test set. So these are structures and compositions that the network hadn't seen. And you can see it's doing a pretty good job, even though we had only 1,200 examples total to train and validate our model with. So as kind of a summary of this part of the research, the main takeaway of this, I think, is that in this case, we're training neural networks that can generalize well to some unseen crystal structures and compositions, as I showed in the final slide, that are going to predict a material's property that's pretty expensive to calculate or measure. All right, so that's sort of one area. And then the other main area that I use neural networks and machine learning methods in is to do some kind of intelligent data analysis. And so I'll talk about this in the context of a specific experimental technique that I work with called coherent X-ray scattering. So I just want to give you a very brief background about this technique so that I can motivate how we introduce neural networks and why they're helpful. So very briefly, in this experiment, we use coherent X-rays. Those X-rays are incident on some kind of a sample that's undergoing some dynamic behavior. And then on our detector that's far away, we observe the evolution of this so-called speckle pattern, which is a reciprocal space pattern that kind of captures at a given moment something about the structure of that sample, which we cannot see directly. We can only observe sort of the signature of what that structure was at a given time based on looking at this detector image. And so the typical way that these kinds of experiments get analyzed is we might do something like correlate the intensities that we measure on the detector at different times. So that's what I'm showing here in that little plot on the right. So what that plot would tell someone is, as the experiment is progressing, our dynamics are slowing down because the correlation times are increasing. Okay, but can we go a little bit beyond this? Can we try and model those dynamics in a little bit more detail rather than extracting correlation times? So that was the question that I posed. And kind of the barrier to getting at those more detailed models of what's going on in the sample is how it's really difficult to try and invert those images back to real space, back to where the dynamics live, because that's a really complicated problem. And so what we want to do instead is to try and use another kind of class of machine learning methods called scientific machine learning to try and model what's going on in real space directly through observations of what's going on in reciprocal space. And so how do we go about doing this? Well, we're interested in modeling dynamics. So one kind of class of neural network approaches that can help us model dynamical systems are neural differential equations. So this is a case where we have some system that some like partial or ordinary differential equation that we don't know, and we actually approximate that with a neural network. And then if we have some observations of what the solution should be in the solution space, putting those together, we can then train that neural network by integrating it numerically at different time points and comparing those to our observations in the solution space. And we can use that to then train the neural network to approximate this differential equation. So I have a very kind of toy example illustrated here where we have this dx dt that's evolving according to some unknown function, but I've plotted it here in the middle where we have our observations of the solution. And then over here on the right is like how that's evolving, how our prediction of that is evolving as we train the network. And here on the far left, you can see how that differential equation approaches the expected ground truth as we continue to train. So this is something, so this is just a simple example to show you sort of what this looks like. And the main advantage of a model like this is that once we've learned this differential equation, we can then go ahead and integrate it even further in time than we observed during training, and extrapolate behavior that maybe is inaccessible to us during the experiment because we have some time constraint, or our sample will degrade, or something that is constraining the time that we have to measure our sample. So this is a very simple example. I just want to connect this to experiments that one might do using this technique. So for instance, the coherent scattering method that I described is used to probe things like light-induced active colloids. So looking at how light affects the behavior and the correlation of these particles. And so on the left, I've done like a simulation that's showing some kind of a clustering behavior of a system of particles. So in practice, we might have some model such as the one shown here that's telling us about how particles interact with one another, but that we might not know explicitly. And so we can model parts of that model, or even the whole thing, with a neural network. So that's called FNN right here. It's approximating some unknown cutoff function in this case. And then we can train this using, again, observations of just these speckle patterns in order to approximate what that looks like. And I want to just highlight again the point about the extrapolation tells us that even if we only train up to a little bit, so here we trained up to a time of 10, but then we extrapolated like to 5 times that. And that correlation function that I looked at before that told us sort of how the behavior of how the time characteristic timescales are evolving looks pretty comparable between the true and the predicted dynamics, which is a good sign. So the main kind of takeaway of neural networks in this context is that here they serve the role of modeling some dynamics that we can't directly observe, or we don't have like good priors for, but that then allow us to extrapolate accurately about how the material is going to evolve, or maybe even generalize to some different initial conditions of the system that maybe we can't prepare. So that is kind of the nature of generalization of these types of models. So with that, I want to thank you all so much for your attention, and please feel free to reach out if you have any questions, and I'm happy to take questions right now. Thank you.
Thank you, Nina. So we have a couple of questions already in Slack that I can read to you. The first two, I think, are more focused on the first half of your talk. Alfred asks, what is the percentage split between data and physics inputs for the initial thing you were speaking to? So like one extreme gives an example. One extreme is 0 data and 100% physics inputs. In that case, it's essentially back to theoretical physics research. Isn't the advantage of data-driven science that we get rid of the theoretical biases?
Yes, yeah, that's a great question. I would say, like in the case that we had, where we had limited data, but we also had expensive physical models. So we needed to kind of strike a balance between the two. So I would say, if you have some prior information that is helpful to the model, like we did, like we knew, okay, we need to obey this symmetry, then it's good to constrain your networks or your architectures in that way. And that typically won't like inhibit their performance a lot. But what it does do is kind of helps compensate for the lack of data. But if you have a lot of data, which I think is kind of customary when we traditionally think of machine learning, if you have a lot of data, then more data is pretty much always better, I think. So that is a huge advantage, and then you should definitely leverage that. I don't know if there's an exact kind of percentage that I would say. It's sort of very problem dependent. But at least in my experience, if you're at the point where you only have 1,000 data points or, in the low thousands, then you probably need some physics. You probably are not quite in the big data regime that you can just expect, a very complex model is going to capture everything that's important.
Excellent. Another question, Jennifer asks, since there's a small data set to work with, do you pick out edge cases to place in your test set, such as small molecules or large molecules?
Yeah, that's a great question. We didn't exactly pick out edge cases, but what we did do is we tried to balance the representation of different elements and I guess volumes of crystals so that there's not a huge statistical discrepancy between what the training set and the testing set are. I think when you do have small data sets, you need to be a little bit more mindful that, your test set isn't just something obscure, something like an edge case, and maybe get really bad performance or something like that. Yeah, that's something that I think is a great point and something that's important to keep in mind.
Wonderful. We have one question that's like a specific situation that maybe you can comment on. IGs asks, when we want to recover missing physics using neural networks from our data set, so coming from solving PDEs, but it's highly imbalanced. So 95% is smooth data and 5% is maybe shock data. And we want to reproduce the spectra. What's your insight on a problem such as that?
Oh, wow. So that's not
if you have one.
Yeah, not sure if I have a good insight into that. I haven't really thought about those types of problems, but so you're saying you're sampling primarily the smooth regime, but then you have some kind of sparse events that are important to capture still. So there may be some kind of a, more sophisticated sampling scheme that you could use to make sure that you're exposing your model enough to those regions and those data points that you don't observe. So, I mean, naively, what comes to my mind is what we do when when we're doing classification problems and we have really imbalanced classes, then we'll try to oversample the underrepresented classes. So maybe that's a little bit naive, but I'm sorry, I don't have a lot of experience in that specific area, but this is sort of where my mind goes.
I mean, a wonderful answer. Okay, UI asks, in general, how accurate are your predictions using ML methods compared to true physics or physical problems? Is there a certain margin of error that's deemed acceptable for the problems that you're trying to solve that determines that you're able to use machine learning, or is it mostly based on computational cost and the amount of data that you have?
Yeah, that's a great question, especially when we're trying to substitute first principles calculations with neural networks. It's important that we know sort of how big of an error is tolerable. So one thing that we looked at in that case where we were predicting those phonon densities of state spectra is, for instance, what is the typical discrepancy that we have between calculations and experiments? And how does our neural network perform in that regard? Because if we have a specific experiment, oftentimes, you'll really tune those calculations to match that experimental data. And so what we found was, unfortunately, I don't have that data on the slides, but we found that the networks are not too much worse compared to the calculations. So I think it's a fair trade-off. If what we're aiming to do is something much more high throughput than we can do with the calculations, I think it is a fair balance.
Okay, I think we have time for one more question. Avery asks, when adding physics to a model, do you know if there's a major difference in physics that typically form a distribution and physics that are more law-based, so like gravity? So I think like distribution, I imagine quantum obviously is mostly just probability based, right? Versus something that would be a a more classical physics model.
Okay, and is there a difference in terms of like how complicated it is to impose those
If there's
constraints?
just, I think, any differences. So complication could be one of them.
Okay. I think there's various ways that you can try and incorporate physics in, like we did here, you know, we imposed a symmetry, like the operations cannot depart from that. So that's a very like kind of hard constraint. But then maybe you can also just do some form of regularization or something, you know, something where if you have missing data in a certain regime, but you know roughly how it should behave, then you just kind of plug in that physics there. So I think there are different ways to constrain, and I don't know if I can give like a very good general answer for this question. But yeah, my I guess main message is maybe that just that there are various ways that you can impose these kinds of constraints in, and it's pretty problem specific.
Yeah. Oh, I feel like this is the general answer to all of these things as people ask. Is like it's almost always problem specific, right?
Yeah,
Depending on
sorry.
like
Yeah.
what kind of like what are your parameters within a neural network to like when you're applying it to a specific like field or like subfield within a field. It's almost always you're going to have to tune as you need, right?
Yeah, yeah.
Okay, I think looking at the time, I think we've sort of hit it. So thank you so much, Nina, for your presentation today. For those of you who are interested in the presentation, we'll make sure that you all have access to it so you can look at it a little bit later. And of course, as you still if you continue to have questions for Nina or for Marieme, feel free to drop them in Slack and we'll continue to have them answered. So with that, thank you all, and we will see you next week.